Hello and welcome back. In this video we will be continuing looking at products of vectors, and the first thing to know is that there are actually two different ways to take the product of two vectors, to multiply two vectors. We can take the dot product and we can take the cross product, and these are using different notation. So if I want to take the dot product of u and v, it's called the dot product, we use a dot. A cross product, we use a little x. It's not really an x, it's just going to be a cross on the page, but the name sort of indicates exactly what is happening there. And something important to know about both of these is that the dot product, when we use a dot product to multiply two vectors, we get a number. So if I take the dot product of two vectors, I'm going to get a number. It could be 0, it could be 10, it could be the square root of 2. It's going to be a number. Whereas the cross product gives a vector. So when you take the cross product of two vectors, you're always going to be given another vector. So this is something important to remember, so that when you're doing a question, you can think, oh, have I gotten the right answer? Well, if you're taking a dot product and you get a number, that's a pretty good indication that you're doing something right. If you take a dot product and you get a vector, that might mean that something else has gone wrong. So let's see, we'll focus on the dot product in this video and the cross product in the next video. So here, we're just going to do a bunch of examples, and here is the formula, essentially the formula for the dot product. When we multiply two vectors using a dot product, we multiply the coordinates. So we have x, the two x coordinates, we multiply them together. We have the two y coordinates, y1 and y2, and we multiply them together to get y1 times y2. And then we add them. And that's it. So x1 times x2, x1 is a number, x2 is a number, we multiply and we get a number. y1 is a number, y2 is a number, we multiply and we get a number. A number plus a number is a number. The dot product gives a number. So let's just do a couple of examples. We have the vector 1, 2 times the vector 3, 4. So what happens is we take 1 times 3 plus 2 times 4 to get 3 plus 8, and that is 11. The dot product of the vectors 1, 2, and 3, 4 is 11. Here we have some 3-coordinate vectors, and the dot product works exactly the same. We multiply it coordinate-wise, so we're going to take 5 times 1 plus negative 1 times 1 plus 3 times 1. So that's 5, minus 1 is 4, plus 3 is 7. And that's all there really is to it. Here we've got an interesting example. We've got 1, 0 times 0, 1. So we multiply the x coordinates. So we take 1 times 0 plus 0 times 1. Well, that's 0 and that's 0. And when we add all that up, we get 0. This is actually a special case that we'll see in a little bit. When the dot product of two vectors is 0, this is important, and it means something in particular. But we'll see that in a little bit. Down here we have some vectors written in the I and j and k notation. So I'm going to think of this in exactly the same way as we were before. We multiply each coordinate and then add them up. So here we're multiplying the x coordinates, so that's going to be in the I direction. So this is 3 times 1. And then we have the y direction, so we have 4 times, and then this guy is negative 2. So again, the 3 and the 1 are the coordinates for the x direction. The 4 and the negative 2 are the coordinates for the y direction. When we multiply these, we get 3, and that's going to be negative 8. So we get negative 5. So here, let's think about this guy. So we've got 2i plus 3j times something in the k direction. So this is in the z direction. So what are the coordinates here? Well, we're going 2 in the x direction, and over here, there's nothing in the x direction. So instead of just thinking about this as k by itself is the same thing as 0I plus 0j, not j, plus 1 times k. So this guy here is this vector. So in the x direction, we've got 0. In the y direction, we also have 0, even though this isn't 0. So we have 3 times 0. And then the last one, there's no k component over here. So this is 0 in the z direction times 1 in the z direction over here. So this is 0 plus 0 plus 0 is 0. And in general, we can think of this in terms of these vectors as well. So I times j, using the dot product, this has nothing in the j direction. This has nothing in the I direction. So it's going to be just like before. We're going to have 1 times 0 plus 0 times 1, which is 0. And this makes sense given the fact that we've already done this dot product. This dot product, it's the same thing as this dot product. 1, 0 is I, 0, 1 is j. So we get the same thing. And then this last one, in the x direction, I and I are both 1. So we get 1 times 1. In the y direction, for instance, that's 0 and that's 0. So we get 0 times 0. So 1 times 1 is 1, plus 0. So we can do all the dot products that we want. So what can we use dot products for? One nice thing is they can be used to find the length of vectors. So when we think about this, if I want to find the length of a vector and I've given it in terms of a coordinate, well, we know that we can find the length of that line. The length which we had normally referred to as r is going to be the square root of x squared plus y squared. And this is why we have the square root coming in here. The dot products, we're taking the x coordinates times themselves, y coordinates times themselves. In a way, this is really meant to make sense. So let's just do some examples and calculate these. So let's find the length of the vector 1, 2. What we do is we're going to take the square root of 1, 2 dotted with 1, 2. When we take the dot product, we're going to multiply the x coordinates, but it's always the same x coordinate. We're taking a vector times itself. So it's the same x coordinate. So 1 times 1 is 1 squared. 2 times 2 is 2 squared. So this is going to be the square root of 5. We've got 1 plus 4. So let's take the length of this three component vector. So we're going to take the dot product of this vector with itself. We're going to take the square root. So this is going to be, so again we have 3 squared plus negative 4 squared plus 5 squared. Again, when we're taking this dot product times itself, each of these coordinates match up, so we're going to take 3 times 3, negative 4 times negative 4, and 5 times 5. So if we have 3 squared, that's 9. Negative 4 squared is 16, so I add to 25. 5 squared is 25, so all of that is the square root of 50. I ran out of room there. Here, if we want to take the dot product of 6i plus 2j with itself, again, we'll get the square root of 6 times 6 is 36. 2 times 2 is 4. So we're going to get the square root of 40. I'm running out of space here, I apologize. And then the length of k. So if I want to take k dot k, well, what we need to do is we need to think, okay, what's the length in the x direction? Well, that's 0. What's the length in the y direction? That's 0. What's the length in the z direction? That's 1. K is only 1 in the z direction and nothing in the other directions. So this is going to be the square root of 0 plus 0 plus 1, and that's just 1. One nice thing is that this is always true for any of the standard vectors. The length of I is the same thing as the length of j, which is the same thing as the length of k. They're all 1. And we saw this before. They're just pointing 1 in the direction of, in either the x, or the y, or the z direction. So taking the dot product can help us find the length of vectors. And we can also use this to find the angles between vectors. So here's perhaps one of the most useful formulas from this chapter. We can take the dot product of two vectors, and this is going to be equal to the length of the vectors times the cosine of the angle between them. So right away, if we are given two vectors, we can find their dot product pretty easily. We can find their lengths pretty easily. So we can find the angle between them. So let's do that for a couple of these guys. So we need to find the dot product of those two guys. We need to find their lengths, and then plug this in and solve for the cosine. So here, let's take their dot product first. So let's take 1 dot to negative 3. This is going to be 1 times 2 plus 1 times negative 3. 1 times 2 is 2, minus 3, well, that's negative 1. So the dot product between them is negative 1. So let's find the length of u. So let's find the length of 1, 1. This is going to be the square root of 1 squared plus 1 squared, and that's the square root of 2. And then the last one, let's find the length of 2, negative 3. This is going to be 2 squared. When we take the dot product, we're taking 2 times 2. We're going to take negative 3 times negative 3. All right, you're going to take the square root. So that's 4, and that's 9, so it's going to be the square root of 13. Now, let's plug all this into our formula. The absolute value of 1 is going to be equal to the length of u, which was the square root of 2, times the length of v, which was the square root of 13, and all this is times the cosine of the angle between them. So if I solve for the cosine, the absolute value of negative 1 is going to be 1, and is going to be over the square root of 2 times the square root of 13. So theta is going to be the inverse cosine of that guy. And this is just something that we can plug into our calculator. I'll switch over to Desmos, and we want the inverse cosine of 1 divided by square root of 2 times 13. And we get 78.69. So it's not too bad doing this. All we have to do is find their dot product and find their lengths, which is just doing another dot product and square root. And what I'll do is do one more quick example. So we've got I times j. So we know that I dot j, this is going to be, I'm just going to write this in terms of coordinates. This is 1, 0, dot 0, 1. And 1 times 0 plus 0 times 1, well, that's 0. The length of these vectors were specifically chosen just to be 1. So when we plug this in, the dot product is going to be equal to 1 times the cosine of theta. So 0 is equal to the cosine of theta. And we know that this happens when they're at a right angle with one another. And we'll see more of this in the next video.